First, we sent in a 90-degree pulse, resulting in some transversal magnetization. Immediately after the 90-degree pulse, we have a maximum transversal magnetization. However, this transversal magnetization disappears due to T2 effects. How fast transversal magnetization disappears can be seen from a T2 curve. The curve starts at 0, which is the time immediately after the 90-degree pulse is switched off. When we wait for a certain time, half of TE, to send in the 180-degree pulse, transversal magnetization will have become smaller. After waiting another half of TE, that is, TE after the 90-degree pulse is switched off, we will receive a signal, the spin echo. The intensity of this echo is given by the T2 curve at the time TE. This time, between the 90-degree pulse and the spin echo, is called time to echo. The time, TE, can be chosen by the operator. And as we can see from the T2 curve, TE influences the resulting signal, and thus also the image. The shorter the time, TE, the stronger the signal that we get from the tissue. To get the best, strong signal, it may seem reasonable to use a short TE, because with longer TEs, signal intensity decreases. With a short TE, however, there is a problem. Let's have a look at two different tissues. Tissue B, water or CSF, has a longer T2 than tissue A, brain. Both T2 curves in this example start at the same point. If we only wait a short TE, TE short, the difference in signal intensity between tissue A and tissue B is very small. Both tissues may hardly be distinguished, as there is hardly any contrast, which is the difference in signal intensity of tissues. Consequence, with a short TE, differences in T2 do not influence tissue contrast very much. As both T2 curves diverge, with a longer TE, TE long, the difference in T2 curves, and thus the difference in signal intensity, meaning contrast, is more pronounced in our example. So it might be reasonable to wait a very long TE. The resulting image should be very heavily T2 weighted. But, and there is always a but, if we wait longer, the total signal intensity becomes smaller and smaller. The signal-to-noise ratio becomes smaller. The image appears grainy. An example to illustrate this signal-to-noise problem. When you receive a local radio station in your radio, this gives you a good signal, for example, loud music and only little static noise. When you drive out of town, the signal intensity of the radio station becomes weaker, and you'll hear more static noise. And when you drive even further away, you may not be able to discern the music from the background noise. And this is the same for the MR signal. There is always some noise in the system. However, when the signal is strong, this doesn't matter much. However, the smaller the signal, the harder it is to differentiate it from the background noise.